I'm here on the job site with Dale, who's a framing contractor.
Hey, good morning.
Dale traded up to Geico Commercial Auto Insurance for all his business vehicles. We're here where he needs us most.
Yep, they sure are.
We make it easy for him to save on all his insurance needs, all in one place, with coverage that fits his business and bottom line. Oh, I shouldn't have looked down.
It's all right.
We're so far up here.
Look at me. Take a deep breath.
Oh, I'm good. So good.
Get a commercial auto insurance quote today at geico.com and see how much you could save. Get more with Geico.
Pretty thighs, shawty, she a dime. Demon girl, evil eyes, she be telling lies. Slim waist,
All right, so today it is my pleasure to interview Dr. Stupp, a professor at Northwestern. Dr. Stupp, thank you for being part of this episode. So can we start with you taking us back and talking to us about your background?
Yes. Well, I am both a chemist and a material scientist by background, and have become very interested in the area of biomaterials for several decades, namely the use of materials as therapies for the human body.
Yeah, so I've had a lot of guests. So I've some guests who are chemical engineers but are able to apply their expertise to biology. So from a chemist perspective, how hard was it to apply chemistry concepts to biology?
Well, it was a very interesting journey, and I have always had a holistic approach about science, and that I've always understood that to really make important advances, you have to know more than one area of science. And I realized this very early on. And so even though I started as a chemist, I then, for my undergraduate work, I went to graduate school in material science, which was at that time was a field in its early stages, and it had been created at Northwestern University for the first time as a field of study. And so my undergraduate advisor told me about Northwestern because I had read about material science, and material science already encompasses many disciplines. So I came to Northwestern to material science, and I was one of the first chemists admitted to the program, in that it was more common for physicists or metallurgical engineers, for example, or chemical engineers to study material science. But I came in as a chemist, and so that already was different.
I see.
So that began the interdisciplinary journey for me. And then, so I learned a lot of material sciences in graduate school. I learned a lot of materials chemistry in graduate school. I learned about polymer science. And then when I became an independent researcher and started my career actually at Northwestern as well for a few years, I then developed an interest in the field of biomaterials. In other words, how could we apply this knowledge to create therapies that or other medical procedures that would really help human beings using design materials. And so that started a new chapter. And I would say that I learned all the biology as an independent scientist. So,
Interesting.
And not by training in school, but by basically doing research.
Yeah. So I have another question. Like, I'm assuming in a lab, do you hire people from not like a chemist background? Do you hire biologists?
Yes, I do.
So how important is that diversity, do you think?
That diversity is critical. So I have created a highly diverse lab scientifically speaking, right? So in my lab, there are always chemists, there are material scientists, there are physicists, there are biologists. I even, for example, I even have a veterinary surgeon in my lab. So I have a very broad spectrum of talent in my lab. And because, the most important things that I've been able to do in my work, I've done them completely within my lab. And as opposed to, let's say, doing some things in my lab and then exporting things to other labs and develop collaborations, which I think is important to do. And I have occasionally engaged in collaborations, but the hard core of my work has been developed internally in my lab. And that diversity of talent has played a very important role. For example, I always have someone in the lab who is more, or more than one person maybe, that is computational, very mathematically oriented. I have others that are more engineering oriented. And definitely, I always have people that know how to make molecules, so they can do organic chemistry, for example, or even inorganic chemistry if needed. And so that diversity has been critical.
I see. So let's talk more about your research. So can you explain like what supramolecular self-assembly is? Because I know it's a very core idea in your lab.
Sure. This is a field that, we helped develop. So, back in the late 80s, I would say, there were some chemists that started thinking about the idea of how molecules interact with each other, and can you predict how that interaction is going to occur, or why, to understand why. Up to that point, the focus of chemistry, particularly organic chemistry, which connects to soft materials, and that's my main area of research, is soft materials. That chemistry was focused mostly on creating molecules, right? How to, synthesizing molecules, or synthesizing monomers to make polymers, and then taking the monomers and doing chemical reactions to make polymers. There was no real emphasis at that time in the idea of understanding how molecules interact with each other, and whether you could create new functions in materials by the way molecules were interacting with each other. So that led eventually in the 1990s to the emergence of supramolecular chemistry. And we were among the first labs to do work in supramolecular materials. We were real pioneers in that area. So there is a seminal paper, for example, in 1993, in Science, there was a paper that we published on making two-dimensional assemblies of molecules. And this is long before anybody was thinking about two-dimensional materials. Now it's a very common thing, graphene and many other constructs that people think about. And 2D materials is a big area of research now. So at that time, we were trying to make two-dimensional polymers, for example, which are, related to covalent organic frameworks right now in 2025. But, that was a long time ago. It was 1993. And so we published a paper on creating two-dimensional materials. And the formation of those materials, the key was understanding how molecules would interact with each other. In other words, we made basically a supramolecular polymer. In other words, we created molecules that created two-dimensional assemblies because of their chemical structure, interacting through chiral interactions among dipoles and hydrophilic and hydrophobic interactions. So that was the very beginning. And so out of that emerged the field of supramolecular materials, meaning that these are materials that you design by considering the interactions between molecules.
We all know that feeling. You finally manage to get away on vacation and the worrying starts. Will that bogus "beware of dogs" sign keep your home safe? What about that fake camera you set up? And will someone finally find your old hide and key rock? That's where ADT comes in. All that stuff, it's safe-ish. It seems fine when you don't really think about it, but you know it truly doesn't work. Instead, ADT provides security solutions that keep you actually safe, giving you real peace of mind. Because vacation is supposed to be, you know, relaxing. Don't settle for safe-ish. Visit ADT.com today to learn more.
Okay, instead of materials that you would design by making primary bonds between molecules, right? Which is how you make polymers, right? It's how you make covalent polymers. When you describe a supramolecular polymer, for example, now the monomers are not connected by primary bonds. They're connected by non-covalent interactions. So these are materials that are designed through their non-covalent interactions with other molecules. And that creates a very interesting new space of materials, which I think right now is emerging as something really important for many new properties. You know, so you have, you know, structural materials, right? Metals and ceramics and right? You have polymers, which have a very bad reputation these days because of the plastic pollution problem, right? So people talk about plastics, right? So all of those are very robust materials, right? They have a lot of structural, for example, metals and inorganic materials. They have highly structured microstructures. I mean, they have very structured, I would say, properties, and they derive their function from those structures. So then you have other materials where, like electronic materials, for example, you know, those have been extremely important for us, you know, in technology at large, and we're going to continue making physical discoveries about the behavior of electrons and quantum phenomena and all of that. And that will continue, right? So that's a very important field, right, for the future. But then there is a new space where for materials that they're not like liquids, right? Which don't have really bonds between molecules. Typically, you know, liquids move around very much. The molecules are very dynamic. And so they're not liquids, but they're not highly structured either. So they're not materials that you're going to use to create buildings or build airplanes, because they don't have, I would say, the very robust structural order that you need for high mechanical properties. But they are not liquids at the same time. They still have some structure, but because the bonds between their constituents are relatively weak, it opens up the field of dynamics in materials. And that is the field, that is the new wave that supramolecular materials are bringing to technology moving forward. They're materials where you can design function based on dynamics, not just based on structural order, which is the more traditional approach in materials, both in the structural sense, mechanically, as well as in the electronic, magnetic, optical sense, right? Because you have highly defined structures in order to give rise to, the physical phenomena that you're looking for in creating, interesting semiconductors and so forth, right? So, but you have to have structural order.
Hmm.
And if you want to have high strength, mechanical strength, you have to have structural order, right? In supramolecular materials, now there is the possibility that you could have some structural order so that you can access certain properties that way. But you also have a lot of dynamics. Molecules move around, right? And we have made key discoveries from these materials. I like to call them four-dimensional materials because where the fourth dimension is time, because they're moving, right? And you can explore the movements and changes in their structure at many different time scales. They could be anywhere from nanoseconds to seconds, right? You can ask questions about how they change in time.
We all know that feeling. You finally manage to get away on vacation and the worrying starts. Will that bogus "Beware of Dogs" sign keep your home safe? What about that fake camera you set up? And will someone finally find your old hide and key rock? That's where ADT comes in. All that stuff, it's safe-ish. It seems fine when you don't really think about it, but you know it truly doesn't work. Instead, ADT provides security solutions that keep you actually safe, giving you real peace of mind. Because vacation is supposed to be, relaxing. Don't settle for safe-ish. Visit ADT.com today to learn more.
Yeah.
And those changes that are possible in what I would call four-dimensional materials, because the fourth dimension is time, give rise to really important properties. And one of so I was really, this is something that I've been thinking about for a while, and started thinking in earnest about this about roughly 10 years ago, about how could the dynamics of supramolecular materials be important in properties. And in the around 2020, 2019, we made a striking discovery, which really fascinated me and it really impacted on my current research right now. And the discovery was that we were exploring supramolecular materials that have bioactivity, meaning that they could signal cells. And this is a subject that we've been very interested in since the year 2001, when we published a seminal paper, which that we can talk about later if you want. But we were very interested in how do you use materials as bioactive structures that can communicate with cells. And so, we've been doing that and developing the chemistry that is necessary. And we came to the conclusion that supramolecular materials that form by self-assembly, guided by their structures, are ideal for this purpose. And this is a very biomimetic idea, because in biology, some of the most important materials that rule life are supramolecular materials, and they form by self-assembly, and they're dynamic as well. The prime example is the cytoskeleton of cells. It's a supramolecular polymer that polymerizes and depolymerizes back and forth and allows cells to move, allows cells to divide, allows cells to differentiate. It's a fascinating thing. We wanted to emulate this. And we made a discovery as we were developing these bioactive supramolecular materials based on peptides, and based on peptides so that they could have signals that cells could understand by interacting with receptors. And we made the discovery that neuroactive materials that we wanted to use to cure spinal cord injury, which is a devastating condition for humans, right? It's one of the problems that we have to solve, because it's a devastating injury, and it's an injury that is becoming more frequent because people are living longer, and so there is more opportunity to have spinal cord injury and become paralyzed. So we discovered in the preclinical model that a supramolecular biomaterial that by design had much more intense dynamics than another similar material with the same signal, similar chemistry, but just by using simple mutations of amino acids, we learn how to make molecules move more. And the molecules that moved more created materials that reverse paralysis after a severe injury in the preclinical model. And very similar materials with the same signal that did not move as much because they had much stronger interactions with each other. So we fine-tuned the interactions between the molecules. We dialed up the dynamics or dialed down the movement, depends on how you want to look at it. We discovered that we could actually either reverse paralysis or not, just by tuning that motion.
Interesting. Because for spinal cords, from other scientists that have been on there, I've always heard of them like putting stem cells.
Exactly. Yeah, but we didn't think that was a reasonable goal yet. It's not that we don't, I mean, we think that stem cells may have an important role to play in spinal cord injury. I definitely think that, but I think it would be a faster solution to spinal cord injury if we didn't have to use cells, from a translational point of view. Because the materials without, not using cells, just using materials that are highly scalable would be a much faster way to solve the problem.
I see. So, for the peptides, why is it called dancing molecules? Because I know
it's the movement, right?
it's the movement.
This came, the history of that was that so we published this paper in Science in 2021, in the middle of the pandemic, we published the paper in Science reporting that supramolecular motion in bioactive supramolecular materials was important in the repair, in neural repair after spinal cord injury, leading to functional recovery, meaning that motor function could be recovered by the animals in the preclinical model when the materials that we used as bioactive materials had a lot of dynamics, a lot of movement. Okay. And so, I mean, that was, and so when the paper was published, I was interviewed by many places. I had an interview, I remember in BBC World News and other places. And it was not so simple to explain this, right, to the media, right, what this was. And so as I was trying to explain that what we had done was enhance the dynamics of the molecules that made up the material, I said, it's almost like the molecules are dancing. I said, they're dancing around, right? They are moving, right? Because the model was so we created these materials that were made up of like very thin filaments, nanoscale filaments, but the molecules within the filaments were translating within the filament or jumping vertically out of the filament, escaping temporarily maybe, and then returning to the filament. So it's almost like the material has life, okay? So it's a highly dynamic material. And those materials were the ones that reverse the paralysis. And then when we slow down those movements, now we couldn't really reverse the paralysis. We could only get a minor improvement.
I see. Yeah. So that's very interesting. So no, for those peptides, how about beyond the spinal cord? Are you looking at, applying it on?
Of course, I'm looking at everything, right now, okay? Because we discovered after that paper that the phenomenon is universal. There's a universality here, right? And so I said, this is a really good mine to look for discovery, right? And we found that all signaling to cells by materials is affected by dynamics in a very special way. So we have models, for example, there are many things, right? So for example, in the biospace, we've looked at cartilage regeneration, we've looked at bone regeneration, where the biologies are completely different, but again, the dynamics are a factor in signaling. So in forming cartilage, in forming bone, which involves signaling receptors, you need these movements, and that's in the biospace. And the reason that these movements are so important is because the receptors in cells, which there's a large diversity of receptors on cells, right? And so things from the outside in the extracellular matrix have to find their targets on the cell membrane. Receptors are moving very, very rapidly in the cell membrane. They're floating, right? And if you're coming in with materials to signal those receptors, then the constituents of those materials that bear the signals that activate the receptors, they should also be moving. And they should also have motion so that they can improve the probability that they will activate the receptors. It's a little bit like what happens in catalysis, right? In classical chemical catalysis, right? You have to have collisions between molecules in order to.
We all know that feeling. You finally manage to get away on vacation and the worrying starts. Will that bogus "beware of dogs" sign keep your home safe? What about that fake camera you set up? And will someone finally find your old hide and key rock? That's where ADT comes in. All that stuff, it's safe-ish. It seems fine when you don't really think about it, but you know it truly doesn't work. Instead, ADT provides security solutions that keep you actually safe, giving you real peace of mind. Because vacation is supposed to be, relaxing. Don't settle for safe-ish. Visit ADT.com today to learn more.
Get a decent reaction rate, right?
Mm-hmm.
You have to have fruitful collisions, right? Which mediated by the catalyst, and you have to have a lot of collisions. So when the material is able to explore many different configurations due to the movements, the probability that the receptor gets activated goes way up. And this is translated in a therapeutic action, which is very exciting.
And your thing be applied to not biology related?
For sure. We just published a paper, last year we published a paper in Nature where we looked at ferroelectricity in materials.
Oh.
And found that this supramolecular, we reported on a supramolecular material that is ferroelectric. And it happens to be based on chemistry that is used actually to create piezoelectric polymers, but it also has chemistry from peptides. It has both. So it's kind of a hybrid material. And we found there that the ferroelectric properties and the diversity of ferroelectric behaviors are impacted by the dynamics. So it's not just a bio thing, it's a pretty general thing. Same thing with the robotic materials that you've read about that we've worked on in our lab, where the purpose has been to create materials that can imitate the behaviors of living creatures, like materials that walk on surfaces or fold, change shape, right? So that you maybe one day think rationally about this, about a robotic function of some sort, right? Where something folds or translates from one point to another, right? In those materials, these dynamics that you and I are talking about are also critical. We have a paper we published a paper in Nature Materials. There are papers in PNAS that we've published recently that show that the robotic behavior is impacted by the supramolecular dynamics.
Interesting.
So it's a new space. It's a new space to look for function. And as I said, you're not going to use these materials to make a new building, to make a building, okay? Right? Or to build a roof, okay? For that, you need structural materials, right? Because they have to be robust. And if you're going to create quantum chips, probably, or you're going to need a lot of, structural order and robustness too, right? For quantum phenomena and so forth. But this is it's a space that it's a biomimetic inspiration, right? That there should be materials that behave like the ones that rule biology, right?
Mm-hmm.
And that hasn't really happened, making PEG hydrogels or, things like that, is not going to get us there, right? I mean, you have to think out of the box here, right? I mean, you cannot, you cannot do these things that I'm describing just with traditional polymers, with covalent polymers. You need supramolecular polymers or supramolecular structures.
I see. So talk more about your robotic soft matter. So you said your next step is to give these soft matter into the brain. So can you describe why it's called a smart material?
The robotic things?
Yeah.
Well, I would love to do that, right? So, and we are thinking every day on how we do it, right? But so for example, we developed this. I was telling you about this ferroelectric material that we reported in Nature last year, and so then this material has peptides.
Yeah.
And it has some chemistry that it was inspired by the chemistry that exists in I would say, the most important piezoelectric polymer known, or piezoelectric ferroelectric polymer. It's called polyvinylidene fluoride. I mean, it's been known since the 1960s. And it makes, they develop sonar technologies and microphones. And there's lots of things. It's a piezoelectric material. But we took a tiny piece of that chemistry, like 6, 7, 8 units, which is not a polymer, it's just a tiny piece, and then built a ferroelectric phase from those conjugated to peptides. So now we have a real soft material, supramolecular. It's not a plastic, right? It's made of small molecules connected to each other by specific interactions, but it's still ferroelectric, still piezoelectric. And we've been, since the first publication, we've been exploring its, how can it help with biological properties, like therapies and things of that sort in the brain, for example.
Yeah, it's really interesting because in neuromodulation, we actually use light to activate neurons. So again, that could be something in the future.
Yeah. So this material is like, it's not a chunk of plastic that you're going to put into the brain.
Mm-hmm.
No, it's going to be assemblies of molecules that are, partly peptide, and then some parts are tiny, so your body can clear them just the way your body clears when you take a drug, made by Merck or by Novartis, right? You swallow this organic molecule that the body it signals receptors, but then it has to get rid of it because it's not metabolized or anything like that. You have to clear it, right? And so the supramolecular material, if there is a part that's not really biodegradable per se, it could be cleared because it's small. and it's not a problem. It's not a chunk of plastic, right? So out of this this material built from very small molecules, you can see the same types of functions that have typically belonged with structural materials or with plastics. But now they emerge in a completely different type of soft matter. And so it's still piezoelectric. So you could just inject them. It's an injectable piezoelectric. I mean, that's kind of exciting.
Yeah, and another question is, can you apply that to like humanoids? Like for example, I know we've heard Tesla, they're making like their own humanoid Optimus. Do you think like these robots could be like your soft matter could be used into these robots?
Yeah, I think it depends on the scale and at what scale, right? Like I mean, again, it's not going to be for like a huge robot that's a structural robot, right? No, I mean not. But if you need something, that has a much finer length scale, right? Maybe microscopic or something like that, right? You may want certain behaviors on the surfaces of larger robots, right? Kind of finer control of what they do at a different scale. It's a little bit like your skin, right? Your skin, is a phenomenal structure, with the way you sense things, how the nervous system, and the brain becomes aware that something is hot right? I mean, those things are going on at very, very small scales. So, right, it's not like a macroscopic finger, the size of a human finger that bends and picks up something. No, I mean, obviously.
Yeah, I mean, the reason why I asked that because I had another guest, I think a year ago that went on. He designed like the first world's living like bio robot. So he's from Tufts. So I was wondering, like, can we apply to those robots?
I think that it is early for me to know what that robotic soft matter that we've developed with supramolecular materials, where it will enter, in terms of technology, what important problems it will solve.
We all know that feeling. You finally manage to get away on vacation and the worrying starts. Will that bogus "beware of dogs" sign keep your home safe? What about that fake camera you set up? And will someone finally find your old hide and key rock? That's where ADT comes in. All that stuff, it's safe-ish. It seems fine when you don't really think about it, but you know it truly doesn't work. Instead, ADT provides security solutions that keep you actually safe, giving you real peace of mind. Because vacation is supposed to be, relaxing. Don't settle for safe-ish. Visit ADT.com today to learn more.
But definitely is not early for the biomaterials part. I mean, for the therapeutic materials that we have developed, that can happen now. That's not for the future. It's something that, so 2 weeks ago we got orphan designation from the FDA for our spinal cord injury, what's going to be the first therapy with these dancing molecules for acute spinal cord injury. We got orphan designation, which is very good for us, and then another material that also based on supramolecular biomaterials got breakthrough designation. So we're talking with the FDA to try to bring those to the clinic.
Yeah, so let's talk about your company. So how do you get into like commercializing your research? I was wondering, was there like a specific person that you talked to or like an investor?
Well, I mean, that these days it's very common for academics to co-found companies, right? I mean, that.
Yeah.
I mean, that's very common, and so it's like it's a trend, that goes back, now probably a few decades, right? And it's just an international trend, I would say, not just US, but everywhere. And it's a very interesting mechanism, right? Because large industries are not always the best place to develop the new technology. Sometimes, these startups are key, right, in developing the concepts, thinking out of the box and being closer to discovery in academic labs. So it's a very interesting mechanism,
Yeah, it
right?
is. It is. Yeah.
Definitely interesting, right? And so, but there are many of my colleagues, have a lot of companies, but I'm not that type, I mean, I'm not like someone that would go out and start 10 companies, I mean, I'm not
Or
that
20
type.
or 30. I know so I know some professors that do that.
I'm not, that's not my phenotype, I mean, but I think it's an interesting mechanism. And so at some point, I said, well, maybe I should look into it,
Interesting.
And so I did and started my journey. And I'm very proud of Amphix Bio, which is the company that I am associated with right now. I co-founded it with my students. And and so I'm very proud of that. And so that's the company that got the breakthrough designation for a new osteobiologic. I mean, it's pretty exciting, because we can grow bone without using the dangerous growth factors that are currently used in some products. But the supramolecular structure activates by design the pathways for bone regeneration. So this will be a really interesting product.
Yeah.
Uh,
So
and then the spinal cord injury, which I'm really excited about. But the neuroactive supramolecular materials that we have right now, using all these new concepts of the dancing molecules and the supramolecular dynamics and all that, we are looking into stroke, ALS, MS, Parkinson's disease. I mean, we're looking at very, very broadly at neuroactive therapies, and it's very exciting, because so we call them supramolecular therapeutic peptides, STPs.
well, it's going to be a new field, I guess.
New field, it's a new field. It's like supramolecular drugs, And I'm very proud of the fact that the spinal cord injury product that we received orphan designation for by the FDA is going to be either among the first or the first. I'm not really sure. I mean, I have to do a lot of research to figure that out, but it's going to be a material that is a drug, a pure drug. It's not a device. It's a drug.
Yeah.
And I'm very proud of that. And I'm hoping that the pharma companies, will see what they stand to gain, So I have to tell you a little story here. So the molecules that we developed for the supramolecular therapeutic peptides are called peptide amphiphils. What's a famous peptide amphiphile of the type that we developed these molecules? I mean, the first paper we published on these molecules is in 2001. It was in Science. It was a real breakthrough paper. Right now, you've heard about Ozempic?
Yeah.
And Monjaro, all the GLP-1, drugs, those are peptide amphiphils. Those are like the molecules that we developed in 2001. And in 2012, so that's 13 years ago, we published a paper on a GLP-1 agonist to enhance insulin production based on our peptide amphiphils. We did that in 2012. So we're a pretty, out there. I mean, and we developed it probably several years before that, but published it in 2012. So those are peptides modified by chemical segments that are hydrophobic so that you can facilitate the self-assembly into a supramolecular structure. So Ozempic is a peptide amplifier, which is kind of interesting.
Yeah, so no, I want to talk about like the grants right now. So I think the government is cutting a lot of grants for science. So how would it hurt startups like Amphix right now?
It's not really affecting Amphix. I mean, because that's a different, mechanism, right? There in companies you need investors, right? You need people to invest, to believe in the technology and see its potential, and then take a risk by investing. So that's a different mechanism, and there's plenty of people in the United States that basically are very interested in investing in new technology. So I think we have a good investment environment in the U.S. So and hopefully that will continue.
Yeah.
Yeah, the problem of the federal government and the universities and all that's a different issue.
Yeah, so just looking back, you talked about how you were kind of a domain crosser, you're a chemist, then you started getting involved in biology. So like what advice would you give to like young people or young science today about the importance of taking risks and like embracing, like trying, other fields?
Yes, I think my advice is to be open-minded and take risks, right? I mean, I took a big risk, when I went into this, to go into the type of science and the type of and create the type of lab that I have had for the last, 3 decades, 4 decades. I took a big risk, because it was not a traditional lab doing, say, polymer chemistry or doing organic chemistry or metallurgy or, I mean, I took a big risk in going into an area that require a lot of interdisciplinary content. And I dedicated myself along with my students to learn all these other fields. It's a little bit like learning foreign languages, And so I would advise young people to be open-minded, to, be ambitious and think out of the box, go after important problems that they want to solve, right? And then ask, okay, so if I want to solve those problems, how do I do it, right? What are the things that might be interesting? Like I always thought, when in early stages of my career, that self-assembly was going to be an important thing. And it is. I mean, whether you use the term self-assembly or you don't use it, there's a huge number of people in the world that use the concept of self-assembly among molecules, right?
Yeah. So how hard was it getting funding for back then, of course?
Back then it was not, I mean, it was a bit of a challenge. But, for example, when I published this paper in 1997 in Science, where we made a molecule, which, so our molecules typically, our constituent molecules they're not polymers, they're not tiny organic molecules. They're kind of, I don't know, oligomers or, medium-sized molecules. They're not too small or definitely not polymers. And so we reported on this molecule that self-assembled, out of solution into mushroom-shaped nanostructures, okay, which then packed into polar layers, which was very counterintuitive, and made a macroscopic film that behaved like an adhesive tape and was also had second harmonic generation activity, was piezoelectric. We found that out later on. And all of that function came from a simple molecule where all you did is you put it in solution and evaporated the solvent and left behind this highly functional material by just letting the system assemble at different length scales, forming a hierarchical structure. I mean, you could take a look at that paper. It's in 1997. And so at the first it was, so like, for example, my paper in two-dimensional materials, which was the first real self-assembly paper, I could argue that we had another one on liquid crystal polymers that was before that one in the 80s. But the real self-assembly first paper was 1993. That paper has been cited only like I would say 200, 250 times, because it was completely out of, it was like totally, it was something that people didn't understand what this was. I mean, it's like, what is this, right? And that paper was pretty much forgotten. I mean, not forgotten, but I mean, it was cited, but not a lot, right? It was ahead of its time. And then when we came back in 97 with this paper I just told you about, suddenly the citations, went up to a much, much higher number. And then a few years later, in 2001, when we reported on the peptide amphiphiles, now a lot of people in the world know about that paper, and it's been cited thousands of times. So you asked me, was it hard at the beginning? Yeah, of course it was hard at the beginning because people didn't understand what this was.
I see. So thank you, Dr. Stupp, for being part of this episode and giving me the opportunity to talk to you so people can know more about your insights into super molecular self-assembly. Thank you very much.
I have enjoyed talking with you, and I hope you found it interesting.
Mm-hmm.